Hey guys, what's up? Welcome back to another paper. So here we'll be doing a complete walkthrough of the AS maths paper. So even for you A2 guys or full A-level guys, you can use this paper. And this is the second paper, which consists of the stats and mechanics only. And yeah, this is really short, hour 15, and there's thankfully only 9 questions to do. So where does it say 9? It says 9 here, so there are 9 questions. But yeah, I'm gonna go break through every question and hopefully clear out any single doubts and explain certain concepts as well. But yeah, without further ado, let's go. So let's start off section A, statistics. Yeah, so there are 5 questions here. So number 1, so Sarah is investigating the variation in daily maximum gust T in kilo N. I'm not sure what the N unit stands for. You guys can leave me a comment for that. For Camborne in June and July 1987. So she used the large data set to select a sample of size 20 from the June and July data. So this could refer to, it's not quite specific here, but I'm probably assuming days because we're talking about the daily maximum gust. So let's assume there are up to 61 days because June has 30 and July is 31. Okay, so Sarah selected the first value using a random number from 1 to 4 and then selected every third value after that. And yep, and so this is basically in regular intervals. What this means is that if you're supposed to select a value of 1 to 4, like for example 3, and then every third value, so if it was going up in sequential order, such as 1, 2, 3, 4, and then 5, 6, 7, all the way up to the last day, say 61st day, then the third value would be going up in the next 3. So adding 3 more, if it was 3, the next one would be 6, and then 9, and then 12, and so on. And this should give us a list of say 20 values or 19 or 20 values. Now that's what it means here. Well, that's what I believe it means. So state the sampling technique Sarah used. So this one is 100% systematic. Something that is systematic means that you want to put the data set in a correct order. You would pick values in fixed regular intervals like they did here. For example, every third value. This is a form of systematic. So it's always regular intervals. Okay, that's it. So B, from knowledge of the large data set, explain why this process may not generate a sample of size 20. Well, if we consider these June and July dates for every single day, as I said, there's 61 days. Let's just make it simple, assume there's 60 days. If we're taking every third value, so in other words, we're going up in 3s, let's just divide 60 by 3 for a second. And here we realize we're going to get exactly, roughly, or give or take 20. Now, this is only true if every single day has been accounted for. So we're not missing any single dates. If for some reason we're missing some days in June and some days in July, there's a high probability that you will not get a sample size of 20 because you're going to be skipping days. And if you're skipping days, it's no longer systematic. And this would be a problem. So this would be the answer. Your answer could be that some days may not have been included. So days in June or July have been excluded or was not recorded in the large data set. That's really what they're looking for here. Okay, now let's move on to the next bit. So the data Sarah collected are summarized as follows. So the sample size is 20. The sum of the t values, the daily maximum gust, is 374, and the sum of the gust squared is 7,600. Now calculate standard deviation. So what I did here is very straightforward. The standard deviation formula is basically the square of the variance. And the variance is the sum of t squared over the sample size minus the mean squared. And the mean is the sum of t over n. I just calculate each one and plugged it in as I went along. This is how I always do it. And personally, I find this easier. If you're not sure how to memorize this one, I would do the mean first and realize that the variance is very similar, except that t is t squared. And then you minus the mean squared. And then to get standard deviation, you just square root your answer. And that's it. That's really it. There's not much I can say here, but other than that, I'll see you guys in the next question. So just want to say one thing. If you guys are enjoying this video, give me a like and subscribe and share to your mates. Anyway, here we go. Number 2. So the partially complete histogram and partially complete table show the time to the nearest minute that a random sample of motorists was delayed by roadwork on the stretch of motorway. Now, one thing you have to note here as well, when they use the term nearest minute, this means that they've already rounded the figure. And this is very important histogram because for histogram, like you see below and the graph as well, there should be no gaps. And if you look at the table, the graph clearly, you can see that for 4 to 6, for some reason they didn't do 4 to 6, they went down to 3.5. And that's how it is. When you round to the nearest minute, it's always plus minus 0.5 on each side. So for each one, we need to update. So 4 to 6 would be 3.5 to 6.5. 7 to 8 would be 6.5 to 8.5. Now histograms, you can't have a single point because then that would just be a straight line which has no weight. In fact, 9 would be, again, plus minus 0.5, so it would be 8.5 to 9.5, and so on. 10 is 9.5 to 12.5. So keep on doing this until you guys get figures like this. I always recommend that you lot do this, yeah? So 15.5, oops. So this is pretty much the main part of histogram. It's always get the figures correct, especially the widths. So there you go. So it's between 3.5 and 20.5 now. Now this is going to be your class width here. So let's just get the figures ready. Class width, number of motors. So this is of course our frequency. So let's call this one F or freak. Now just to understand histograms, and before we complete this, I think it's best we complete this table first and complete the chart. Now, and you'll notice that on the y-axis there is no values given except 0, so we don't know the actual height, but it's very easy to calculate the height. For any frequency density, always draw this kind of nice little graph. Just put this nice block and treat this like a rectangle. Let's say that the area is called the frequency, yep, which it is. That means the width is the class width, which is the width, and the height is the frequency density. So these are 3 units. So we can say frequency equals frequency density times a class width, just like base times height equals area. Now looking at each one, we have some frequencies. We know that between 3.5 and 6.5, the area is 6, which is this region here. For between, what's this one? 12.5 to 15.5, which is this column here, we have the area which is 9. And I think that's all we're given. Yeah, that's what we're given. So what can we do with this information? Well, since you know that the area is given, we can therefore find the height. So if we know that the area is 6 and we know that the class width, so we got a width of 2, we have a width here of 3, because between 3.5 and 6.5 the width is 3. So 3 times something gives us 6. Well, we know it's going to be 2. So we can kind of see that every block is going up in 1. So this area, this height here is going to be 2, 4, 6, 7. I hope it's 7. 2, 4, yep. This one has a height of 3. I'll put 3 in the top. This one has a height of 1. So let me just put the numbers at the top here. That's it. So if we have the height, well, we can find the area. So this height is 7 and the width here is clearly 2. So 2 times 7 is 14. This one has a width of, what's this? 5. So 5 times 1 is 5. And I think we're done. So we just fill it up. So the last column is 5. So put 5 over here. This one here we found is 14, so put over here, and we're done. Now all we need to do is, what do we need to do? We just have to draw the histogram for 8.5 to 12.5. So we know 8.5 to, okay, we got 2, we got 8.5 to 9.5, the area is 17. So this has a unit of 1, but a height of 17. So if the width is 1, so let's say up to here, that means 1 times 17 will give us 17. So we have to go all the way up to 17. So let's see, 7, 8, 9, 10, 12, 14, 16, 17. So it'll be 17. So it'll be between here to here. So this will give us a complete, oops. So yeah, use a ruler, yeah. This will give us a complete height of 17. Next time I think I'm just going to complete this one in advance and just explain to you guys. I think that's a lot easier. So this would be our 17 area. We can see that 1 times 17 is 17. Now for the last bit, let's have a look. Between 9.5 to 12.5, which is this column here, we know we have a class width of 3, so that the class width is 3, and the area is 45. So 3 times something 45, well, it'll be 15. So the frequency density, I should have put it here. So 3 times 15 gives us 45. So we need a height of 15. So the width is 3, we check, so it's from here to here, and a height of 15, which is about here. So let me label this 15, and this was 17. And that's it, guys. I think this is done. So just draw your shape and then just label it. That's it. All done. So let me just put the heights there. 17, 15. Area is 17. Area 45. Yep, that's really done. Now, what was the question? So estimate the percentage of these motorists who were delayed by the roadworks for between 8.5 and 13.5 minutes. So essentially that's from here, 8.5, so that covers it. So it'd be 17 plus up to 13.5 plus this as well. So 13.5 lies between 12.5 and 15.5. So if we look at 12.5, 15.5, we can just split it 13.5 to be here. So this would be the limit. So if the whole area is 9 and if the width was 3, the width is now going to be 1. So 1 times 3 will give us 3. And this of course be 6. Another way you can look at this is that this is just 1/3 of the area. So we've got 3, so we just take 3 from here. So 1/3 of this will be 3. So it'd be 17 plus 45 plus 3. And that gives us 2065. So this means that the percentage of motorists who were delayed by the roadworks for between 8.5 and 13.5 minutes was 65 over the total number of motorists, which I already calculated was 96. So it will be 65 over 96. And if you put that in the calculator, you should get about 67.7%. That's it, all done. So yeah, let's move on to number 3. So if you guys are enjoying this series so far, again, give me a like and subscribe and share with your friends. Now here we go, number 3. So this one's gonna be super easy. So the Venn diagram shows the probabilities for students at college taking part in various sports. Okay. Now A represents the event that a student takes part in athletics, T here represents tennis, and C represents cricket. And then they gave us a couple unknowns, which were P and Q. So one thing to know about Venn diagrams, everything inside the Venn, including the inside the circles and outside the circles, must total up to 1 or 100%. So it seems okay. Now, the probability that a student selected at random takes part in athletics or tennis, in other words, in the areas of A or T, equals 75%. So before we look at the questions, we know that everything inside here is 75%. So this means Q plus P plus 0.40 equals 75%. So let's just put all of these out here. This means that the outside these circles, this will give us a remainder, which will be 25%, because 25 and 75 give us a whole. So this means these two, 5 and P, must add up to make 25%. So this means we've already got 5% on here. This P value must be 20%. So P is automatically 0.20. So this means this P value is also 0.20. And if we know that all of this is 0.75, doing some quick maths, this gives us 60. This means that we must need 15 more. And yeah, it looks like we found P and Q. So find the probability of the value of P. Well, we knew is 0.20. Now state, given a reason, whether or not the events A or T are statistically independent. So statistically independent literally means if the probability of A times the probability of T equals the intersection between A and T. So we need to prove that by doing the probability A, which is 0.35, and the probability of T as a whole, which is 60 by the way. When you multiply them, we need to check if it gives us an answer of 0.20. So I did it over here. I can show you my diagram. So this is the result of the Venn. It looks a bit like this. So updating all the values and making it look nice. And this is the assumption. We need to prove that A times T gives us A and T. Well, looking at the left hand side, 0.A, which is 15 and 20, gives us 35. And T, which is 20 and 40, gives us 60. Multiplying them together will give us 0.21. So no, they're not independent, because 21 of course isn't 20. And that's it. That's what you say. 3 marks for that. And lastly, guys, I know I'm doing this super fast. For part C, we need to find the probability that a student selected at random does not take part in athletics or cricket. So a student does not take part in athletics or cricket. So we're looking at someone that isn't part of the A circle, nor is part of C, meaning you're left with 40 and 5, meaning the answer is 45. That's it. Let's go. So what do we have here? So Sarah was studying the relationship between rainfall given in R millimeters and humidity in H percentage. So I can already see that there's some sort of correlation regression problem coming up in the UK. She takes a random sample of 11 days from a specific month, so May 1987, for Luchars. I hope I said that right, guys. Anyone from that, forgive me. From the large data set, she obtained the following results. So just having a quick look at the results for 2 seconds, you can see that for humidity, it seems to be quite consistent between 80s and 90s. So, of course, you're in May, so it's summer. So you expect this to be the case. So we expect it to be quite humid. As for the rainfall, it seems to be quite consistent, like very low, 1 and 0. But, oh wait, hang on. Yeah, you got 20.6, which is obviously messed up. And yeah, so more or less, to summarize, you should try and spot that 20.6 is obviously going to be an outlier, which will come up in a question anyway. So let's keep going. So Sarah examined the rainfall figures and found out that the first quartile, so out of the 11 days, the first quartile of it was 0.1, the medium was 0.9, and the third quartile was 2.4. Now, a value that is more than 1.5 times the interquartile range is above the third quartile is called an outlier. So they actually define it for you what an outlier is. In other words, I wrote it here. So it's basically 1.5 times the interquartile range. And remember, the interquartile range is the difference between the third and the first quartile. It's the range between the upper and lower quartiles. Make sense? And of course, it's above Q3, so plus Q3. Now, show that the value 20.6 is the outlier. Well, first things first, we have the value Q3. We have 1.5, and IQR is just 2.4 minus 0.1, so 2.3 here. So you just plug all this in, you realize you should get 5.85, and well, any values above 5.85 would be considered an outlier in this experiment. So 20.6 is clearly above. That's what you should say. You can say clearly 20.6 is above this formula, which is above 5.85. Simple. It's kind of obvious anyway, but we have to use mathematical proofs. Now B, give a reason why Sarah might exclude this day's reading. So we're talking about 20.6. Well, from what I gathered, if you're going to put a data set, usually when you record, you keep. So in many cases, you should choose, if you choose to include it, you keep it because the data set could be relevant and it helps possibly build a complete picture, even though it could be an outlier. However, to exclude it, which is quite simple, the value itself could just be a mistake or an error. That's really it. It could have been a typo. It could have really been 2.6, like 2.4, but we don't assume that. That's really it. Now, next one. So Sarah decided to exclude this day's reading. So now we only got 10. So she's just going to exclude it. So 97, 20.6 is gone. So we only have 10 pieces of data. And she decided to draw the following scatter diagram for the remaining 10 days. Okay. So very easy. You got humidity on the x-axis, rainfall on the y. So we're probably going to guess that y depends on x. So rainfall depends on humidity. So looking at this one, it's hard to probably visualize, but this is sort of like a positive correlation, maybe. And what does this tell us? Well, we have to firstly give an interpretation of the correlation between rainfall and humidity. So all I just said, if as humidity increases, then the rainfall increases. So as H goes up, rain goes up. So in your answers, it's best to say that this diagram, you could say firstly that there is a positive correlation between humidity and rainfall. And in turn, this implies that as humidity increases, rainfall is expected to increase. It's kind of weird, isn't it? But yeah, that's how it works. Now, next one, number 4. So the equation of the regression line of R on H for these 10 days is given to be R equals minus 12.8 plus 0.15 H. So just like your standard straight line equation. So this is talking about this line I just drew. Okay, something like that. Now, give an interpretation of the gradient of this regression line. So I put the answer already here, but just to understand, we're talking about this figure here. So because we can see that the gradient is 0.15. So what we have to understand is that for every unit of H, you get a total rainfall of, you get an additional 0.15 millimeters of rainfall for every 1 unit of H. So that's all you have to understand. Every time you increase this value H, the total rainfall will also increase. So here is an example answer. So an increase of 1 unit or 1% of humidity causes an increase of 0.50 millimeters of rainfall in this specific calendar. So it's good to specify where. This is only specific to May 1987 because that's a day set we have. So of course she only took a random sample of a days fixed from May. If you took the whole year, then this would obviously not apply. And yes, I should have said May 1987 for Luchars. Again, if I'm saying it right. So that's what you should do. Secondly, actually that's it. And yeah, I gave an example. So the one way to understand is that it's best to use values between the ranges. So humidity, we know that humidity lies between what, like the 80s and 90s. So just plug in values of 90. I just chose 91 and 92 just to show that there's an increase of 0.15 as you go up by 1 unit. Not necessary, but just to have an idea behind this. Now E, comment on the suitability of Sarah's sampling method for the study. Well, this is not suitable for everything because remember, we're focusing on the specific month and year, so May, and that specific region, Luchars. So we could say that it's not suitable for other months and locations. Of course, it's only suitable for that particular month, and only 11 pieces of data were used solely in May, or in this case I should have said 10 because we used 10, we ignored the other one. So it's not very reliable. It's only suitable for May and between those ranges. Now, suggest how Sarah could make better use of the large data set for a study. Well, I said that large data set should include other months and regions because in general, to improve your data, it was always good to consider every single, it depends how far you want to go. If you want to include every other month and region, then you would have a complete or clearer picture. So doing so, this would improve the accuracy and reliability of the data. Then this is a good use of using a large data set. She could use the company's data set, of course, a large data set, and consider data sets from various location months. That's literally all you need to do. And because it's only what, 2 marks, this should give you more than at least 2 marks or more. Well, 2 marks. But yeah, that's really it. I mean, if you guys got any question on this, feel free to drop me a comment because this is all theoretical. So we're not really doing any proper maths here. This is all your understanding on correlation and regression. That's really all it is. But yeah, let's go. Let's how about we move on to number 5 now. Oh yeah. Oh, now this one's kind of annoying. I can't lie. Now, when I wrote this here, there's a specific calculator that you guys need to buy when you're doing the binomial distribution, or normal, or Poisson, or whatsoever. And this is the FX991ES. So I made a little link to Amazon. I could put this on. I'll attach this calculator actually on the description comment. And you guys should really buy this because this includes everything you need for the new specification exams. So the old ones unfortunately doesn't work, and it's recommended to buy this calculator. So keep an eye out on this one. Otherwise, you cannot solve the first question. Was there questions? Yep. Otherwise, you cannot solve part A because we're given a binomial distribution with n40 and probability 0.27. You cannot solve this question. You can, but it'll take you a long time. These questions are made for the calculator. Okay. So I would have a breakdown on this one, but it's best. The general idea is that because you got a probability which is greater equal 16, we have to convert into something that is cumulative. So it'll be 1 minus less than equal 15. So instead of 16 and up to 40, it'll be 15 and less to 0. And in the calculator, this is known as the cumulative probability, which is available in this calculator. Otherwise, you're going to have like 15, you go do 15 different calculations if you do it manually. Unfortunately, you cannot use interpolation if you guys have thought about that. Because in the tables, and I also want to do this really quickly, the tables only record probabilities in going up in 5%. This one only records this one has a probability of 27%, so that is not on the table. So again, don't use interpolation because I tried it and you don't get the correct answer, which is 0.0509. You get 0.0618, which is close, but no cigar, guys. But yeah, that's it. But anyway, besides that, buy this calculator and it should be fine. But anyway, skipping part A, the rest you can do without calculator, thankfully. So what do we have? So it says past records suggest that 30% of customers who buy baked beans from a large supermarket buy them in single tins. Now, this new manager suspects that there has been a change in the proportion of customers who buy baked beans in single tins. So keep this in mind. So we got a probability of 30% who buy baked beans, and that's fine. And now we got a random sample of 20 customers who had bought baked beans. We also know that another key thing to note here is the wording. So sometimes you might hear the words that, the manager suspects that there has been an increase or a decrease. In this case, he uses the word change. So he doesn't know if it's increase or decrease. Hence why when you get to part B, you'll see. So for part B, write down the hypothesis that should be used to test the manager's suspicion. So all you have to do is say, okay, let's get a null and alternative hypothesis. So H0 and H1. We know that the null is 30%, so P equals 30% or 0.30. The alternative would be P doesn't equal 30% because there's a change. So it's not greater or less, it's not equal. So in other words, this is also known as a two-tailed test. okay, because it could be up or down. So anyway, that's done. Part C. So using a 10% level of significance, okay, and this is two-tailed, so we're looking at 5% because it's halved. It's 5 on the left, 5 on the right, so up and lower. Find the critical region for a two-tailed test to answer the manager's suspicion. You should state the probability of rejection in each tail, which should be less than 5%. So first things first, we need to know what our binomial distribution is. We know that n is, the sample size is 20, so n is 20, and we know the probability is 30%. So now we need to, the key idea is to find what value, or what sample do we need that will guarantee probability less than 5% on left and the right side. So diagram wise, it looks a bit like this. So suppose you have this entire sample. We want to find it on the tables a percentage less than 5%. So let's have a look. It's probably best to go through this step by step. Okay, so firstly get this table out. N is 20 and P is 30%. So on the tables here, guys, so I've got it ready. So look at the binomial table, and if you guys are not sure where this is on the Pearson Edexcel website. They have a formula table ready for you guys. So okay, let's look at n is 20, perfect, and then the probability value was 20, it was 30%, so 0.30. So you scroll down, and now we find a probability value which is less than 5%. So we see that we have 0.0355. This is 3.55%, so less than 5. But afterwards, it's bigger than 5, it's 10%, and so on. So that means we know that the first critical value is less than 2, which is 2. Remember, this is a cumulative table, so this is probability x, or y in this case, less than equal to. Another thing we'll spot now, and because it's two-tailed, we have to look at the right side. So remember, just think of it as a bell shape. We have to look at the remaining 5%. So if probabilities go up to 1, we need to look past the 95%. Okay, so between 95 to 100%. And if you scroll down, you'll see that if the probability value here, 0.9520, is literally just above 95%. So this is the last 5%. So yeah, you'll see that this value is literally the remaining 5%. But if you think about it, because this is a cumulative distribution, this is telling you that the first, 9 values accumulate 95%, over 95%. So that means the values after 10 will accumulate the values less than 5%. So we're going to have to look at probability y greater than or equal 10. So remember, it'll be these values after, yeah? So that's it. So that means we have a critical region, which is y less than 2 and y greater or equal 10. Whew, you know, guys, stats, it's okay, but it takes a while to really break down. But yeah, that's what we got right here. Okay. Whoa, sorry, I just got a crazy neighbor, just God knows what he's doing. Okay, D. Find the actual significance level of a test based on your critical region. So this is dead easy. This is just basically the probability values of what you just found. So that's what it means by actual significance level. So if we realize we had the probability y less equal to, it was like 3 point something, wasn't it? It was this value here, 0.0355. So that's the value for this one, 0.0355. And probability y greater than or equal 10. Well, we know that when y was less than or equal 9, it was 0.9520. So greater than or equal 10 would be 1 minus this value. Okay, so 1 minus 9520. 9520. And if you add them all up, if you solve this, add it to the first, you should get this value here, which is again less than 10%, but they want a percentage. So make sure you get the percent, or else you could lose a mark. All right, so far so good, guys. Almost done. Now, one afternoon, the manager observes that 12 of the 20 customers who bought baked beans bought their beans in single tins. All right. Comment on the manager's suspicion in the light of this observation. Well, this is all based on the critical region. And remember, if you look at the part C, we're talking about the critical region to test the manager's suspicion. Well, if it's above 10, then we can safely assume that the manager's suspicion is supported. So if for anyone that has 10 or more people, or 2 or less, then we say yes, we support. And that's it. So we say 12 greater than or equal 10, all good. Now finally, later it was discovered that the local scout group visited the supermarket. So remember, these are not random. So these are specific people that often to buy food for their camping trip. So it wasn't random, they know what they were doing. Comment on the validity of the model to use to obtain the answer to part E, given a reason for your answer. This is very straightforward. One thing you need to know about binomial distribution is that the sample size is random, and you spot the words here, a random sample 20. If you have a random sample, it's binomial. This one is not random, so it's not binomial. And that's it. That's all you have to say. Binomial is not valid as it's not a random sample. And that's it, guys. I hope these stats questions helped. And after this, we'll be looking at mechanics. So hit me up and let me know what you guys think. And otherwise, I shall see you guys next time. Ciao. Hey guys, welcome back to another one. And here we're going to be working on section B of mechanics of the sample 2017. And I'll be honest with you guys, I had a quick browse through this paper and done the majority of the questions up until this recording. And I could tell you instantly that this paper, at least mechanics, is probably the easiest part of the AS course. It's actually very straightforward. But anyway, let's have a go and try and break everything down. So let's have a look. So unless otherwise indicated, whenever a numerical value of g is required, take g equals 9.8. So guys, there is a clear mark scheme on this. If you happen to use the value of g equals 10 or even g equals 9.81, you would actually lose your marks. You actually get penalized for using a wrong value g or a value that isn't 9.8. And yeah, I know it's silly, but it happens. So let's look at number 6. So a car moves along a straight horizontal road at time t equals 0, so over here, the velocity of the car is u. Okay, let's just call this line over here a. So actually I might just do it right now. This is already solved, by the way, but I'm just going to show you just as we do it for t seconds. So from here up until t, the car travels a distance d meters during these t seconds. Now fig 1 shows the velocity time graph for the motion of the car between this time interval, so from 0 to t. Now using the graph, show that you can make an equation from the distance, which includes ut plus half at squared. Okay, and guys, you get no points for using any of the formulas and substituting in, because it doesn't work like that. We want to basically derive it from just looking at it. Okay, so first things first, and I've actually already solved it here. The key idea is to try and firstly give as many notations as possible. So what I did, we've already got u and t, and we drew the acceleration here. We might as well give this point here a name. This coordinate here, I just realized that this is the highest speed, so I just called it v with a capital V. Okay, just indicate that this is the speed when it reaches this point at time t. So effectively, we have 2 points. We have a coordinate here which is at a time of 0 with a speed of u. We have a coordinate here at time t with a speed of v. Now, first things first, notice 2 things. Because we want to find the distance is calculated as the area under the curve, or under the shape basically. And because this is clearly a trapezium, we can just firstly work out the area of a trapezium, and that will give us our distance. So that will be one equation. Our second equation involves acceleration. So notice how we can calculate acceleration by considering this as a gradient of a line. If you can work out the gradient from 0u to tv, then that's it. You pretty much solved it. You pretty much got the 2 components, plug them together, and you've literally proved this equation. Okay, so first things first, let's look at the trapezium. So the formula is always the sum of the 2 parallel sides. So over here, if you consider this length here, so this is u, and this length up to here is v, so I got u plus v. It's the average of those 2, so that over 2 times the perpendicular side. So from 0 to t, so the distance is t. So that's why we have u plus v over 2 times t. That's easy. Now, as for the acceleration, the gradient is always calculated as the change in y over the change in x. In this case, our y is our speed and our time is t. So change in v over change in t. Now, the change in the y coordinates is v minus u, and the change in x coordinates is t minus 0. So that's it. And all of that equals a. Now, what you want to do here is realize that the final equation does not have a capital V. So my tip is to firstly make capital V the subject of one of these formulas. I'm going to do it on the second equation because it's easier. And plug into the first equation, the D equation, and you're done. So check it out. So here's our first and second equation. So firstly, the target is eliminate V. So firstly, times T across and make V the subject plus U across. When you do that, sub this into the first equation. So replace V with AT plus U. And it should look something like this. Collect the like terms aside. So you got 2U plus AT. Expand the bracket and you're done. And then just tidy up a bit. Put A there or 1 over 2. And we did it. That's literally the final equation. Yeah. So if you guys found this video helpful so far, I mean, give me a like and share with your friends. And of course, definitely try and make sure you subscribe as well. Otherwise, let's move on to number 7, which by the way is super easy too. So here we go. A car is moving along a straight horizontal road with constant acceleration. There are 3 points, A, B, and C in that order on the road, where A, B, the first point, which I drew over here, which is 22 meters, and from B to C, which is 104. So guys, always make sure you sketch this as you go along. Makes life easy. And of course, draw the acceleration going from A to C, okay? Now, the car takes 2 seconds to travel from A to B, so I labeled it 2 seconds here, and 4 seconds from B to C. They did not give you the speeds yet, so I just called it the speed at A, which is VA, VB, and VC. Now, they want us to find the acceleration of the car, the constant acceleration A, and the speed of the car at point A. So that's really it. So essentially, I could just cross out these ones right here because we don't really need it in this question. So what do you do? So my tip is to firstly pick a suited formula that does not have V, because if you notice, we do not have. So this is essentially can be considered an initial speed U. If you want to find the speed at A, is the initial speed. So we need a formula that has an A, an acceleration, a time, a distance, and a initial velocity, initial speed. We do not want V. Okay, so just pick the one that isn't V, and it turns out you'll find the formula to be S equals U2 plus half AT squared. Now, what you could summarize from this diagram is a couple things. We could measure from A to B, which has a distance of 22, and it takes 2 seconds. The acceleration we're trying to find, so it's a question mark, and the initial speed can be U equals VA. Now, I wouldn't use B to C because they don't want you to find the speed of B or C. They want you to find the speed of A. So you could do from A to C, which has a total distance of 126 meters, which is here, and a total time of 6 seconds. And of course, the initial speed is obviously the same because it's the same starting point, and the acceleration is of course the same because it's constant. And now all you do is plug these both into the formula here, so make 2 different equations, one for the first like I did here, when S is 22, T is 2, and the second with S is 126 and T is 6, and you get basically simultaneous equations. Now all you have to do is literally solve this simultaneously. So this is pretty much GCSE stuff now. So a quick way to do this, just multiply the first equation by 3 so you can match up the U coefficients, so you get 6 U's, and then subtract the third equation with the third equation with the second equation, and then that should eliminate the 6 U's. 18A minus 6A is 12A, 126 minus 66 is 60. Divide 12 and boom, you have your acceleration. And then plug in your A value into, well, any pair, and you should come up with a speed at point A of 6 meters per second. And that's it, done. Literally, like I said, this question was easy, and this paper is too easy. It's really damn easy. But yeah, if you guys enjoyed it again, give me a like, and otherwise I'll see you in question 8 now. Alright, let's go. So a bird leaves its nest at time t equals 0 for a short flight along a straight line. Now the bird then returns to its nest. So definitely pay attention to what's happening. It's a straight line. Bird goes from here, so at time 0, goes somewhere here, and eventually it comes back to its nest. So this is a straight line, something easy, yeah? Now the bird is modeled as a particle moving along in a straight line. The distance s meters of the bird from its nest at time t seconds is given by this. So what this is telling us that the general displacement, because remember s is displacement or distance, from its starting point. So depending on the time, it moves at a certain point and then it will return to its displacement. Okay. Now this is the part where everyone is literally a bit confused. Explain why we have a restriction. Well, so just like I said earlier, the variable s is the displacement from its initial point. So basically the distance the bird traveled from and for flight to come back to its initial point. Now what I just realized is that you could just simply factorize this equation, and you want to pretty much prove that when t is 0 and t is 10, you should get a 0 displacement, meaning it's returned. And because it's returned to its initial point, we should have no displacement. Now the reason why it's between 0 and 10 is because any t value between 0 and 10 will give you a positive displacement. Technically, if you put values like 11 or 12, you would get displacement too. But the thing is, we know it ends at 10 because once it returns to its nest, it doesn't move again. It stops. Because it says then returns to its nest, meaning by the time it stops moving at time 10, it's not going to move again. So that's why we're stuck at time 10. Now, So yeah, I mean, you could just do algebra, factorize this, simplify this expression. I took out t squared and then factorize the inside and realize it's a quadratic with t minus 10 squared. And then you can just clearly say that, you know what, when the displacement is 0, basically when it's at its nest, this occurs at time 0 from basically its starting point, or time 10 when it returns. That's really it. And of course, like I said earlier, s is positive between these values because why? Mathematically speaking, every term is squared. So any value here will return a positive value, so it's positive. Yeah, so it's not bad. I mean, you just have to just be careful how you explain. You always relate to the context of the information, and of course, try and bring in as many mathematical proofs, and that helps a lot. All right, so let's look at B now. Let's find the distance of the bird from the nest when the bird first comes to instantaneous rest. Now, be very careful with this. When it says instantaneous rest, this means as soon as the speed hits 0, after it's moved. So we're not talking about the time it did not move in the very beginning, because then that would be no displacement. We're talking about as it traveled at some point in time, it eventually stopped to take probably a break. We want to find that distance from the initial point. Now, thankfully, because this is an equation, and one thing I love about this new mechanics is that if you differentiate this, you'll get the velocity. And then you can set that velocity to 0, just like your standard dy of dx equals 0. Well, I'll show you here. So what I did, let velocity equals ds over dt, differentiate this, and the cool thing is, to differentiate it comfortably, remember 1 over 10 is a constant, so ignore that. You just differentiate the inside of the bracket. So t to the power 4 becomes, you drop the power 4, so you get 4t to the power 3, drop the 20 down, you get, drop the 3 down, and you get 20 times 3, which is 60, this becomes a 2, drop the 2 down, you get 200t, and that's it. And now you say when speed is 0, i.e. when it's at rest, then this happens. Then all of this is set to 0. And you just solve for t. This is a cubic, but I mean, just have to factorize t out and then factorize a quadratic expression here into 2 other terms, and you're done. And then you realize that you have 3 solutions. Now, it's very important to understand what each solution means. The first solution, when t is 0, implies that you are at a starting point, so this is not the first time. This is probably when the bird began to move, just before it moved. Now, this is the first time at rest, at time 5. So when time is 5, this is the first time the bird decided to chill, to probably hatch his eggs or get some food. This is what we want. And lastly, we got t equals 10, and this is when the bird returned to his nest. So of course, there's no displacement. So the only suitable answer is t equals 5. So when you plug in t equals 5 into the displacement equation, S equation, you can find out exactly how much he moved, or she. And the answer should be, well, I don't know if it's right, 6.25 meters. Plug it in and see what you guys get. I didn't check the solution for this one, but I think it was 6.25. Anyway, I hope this helps. And oh yeah, I put a note here as well. You don't have to put this, but this is clear. When t is 0, t is 10, you get no displacement. But yeah, I hope this helps, guys. And if you enjoyed this video, please give me a like, any feedback, and otherwise, stay tuned for the final question. Ciao. So I had a quick look at this question, and I've already solved it as usual. And overall, it's actually quite straightforward. There's nothing new about this question. It's just typical resolving forces, perpendicular ones, a typical 2-pulley system. If you've done the previous M1 papers, then this will come to no surprise. It's actually a lot easier than those even. And there is no complicated question as in how far does A travel, or when does it hit the pulley, etc. You get nothing like that. This is very simple final question. But anyway, let's have a look and try and walk through all of this. Yeah, I'm going to go ahead and label this diagram as I'm reading the text, and we'll compare it to the final diagram and use it to solve the rest of the problems. So let's do this. So let's begin. A small ball A of mass 2.5 kg is held at rest on a rough horizontal table. So here's the mass A, and with these kind of diagrams, always draw forces. So here I'm going to draw a downward force because it's held at rest, and that's representing the weight of 2.5 times the gravitational value of 9.8. So that's done. And of course, just looking at B, we can put 1.5 g here as well. Easy stuff. Now the ball is attached to one end of a string. Okay, so since this is a string, we have to assume that there is some form of tension coming off it over here, and of course tension here. Oh yeah, by the way, because this table is rough, there is also a force going back, like that's on the ground. So this is the rough ground. Okay, so there is going to be some friction. Now we don't know if there's a value yet, so we're going to keep reading. Now the string passes through a pulley P over here, which is fixed at the edge of the table. The other end of the string is attached to a small ball B of mass 1.5 kg hanging freely, okay, and it's vertically below P, with a height of 1 meters above the ground. Now the system is released from rest. So if it's released from rest, there's a good chance that this ball is going to slowly go down, dragging this one with you. Okay, with the string taut. So taut means it's tight, so the string isn't slack at all. The resistance to the motion of A from the rough table is modeled as having a constant magnitude of 12.7 newtons. So that's the resistance, that's the friction. So we don't even use the mu coefficient here. We actually have the full force. Like I said, it's easy. Okay, and yeah, because we know it's moving due to acceleration, and the B is going to fall down, we're going to put some acceleration factors here going downward, because we know A travels horizontally and B is falling down, so it's going downwards. Okay, so always label it down as much as you can. Okay, let's keep going. Right, so the balls are modeled as, okay, ball B reaches the floor before ball A reaches the pulley, so that's cool. So we can say that the distance from A to P is greater than 1 meters. Now the balls are modeled as particles, and the string is modeled as being light and inextensible. The pulley is modeled as being small and smooth, and the acceleration due to gravity G is modeled as being 9.8. Standard stuff, very standard. Now A, write down an equation for motion of A and for B, and B, hence find acceleration of B. Okay, so I'm going to do parts A and B together. Now the first thing I want to look at is firstly, how do we model equations? Well, we always model in the direction of the force, so going right. So we always model the direction going right at A, and we follow the acceleration at B, so we resolve going downwards for particle B. Now I'll show you what I did here. So this is the same thing. Got the tension T, so I don't know if I even labeled this tension. Yep, I did. Now resolving at part A, so we're resolving to the right. We can see that if we're resolving to the right, that means the tension is positive and the value behind is negative, so T minus 12.7, and it always equals MA, mass times acceleration. So it's always the resultant force equals mass times acceleration. So mass is 2.5, acceleration is A. Now I'll do the same for the downward force. So resolving downwards, i.e. following the acceleration, we have the resultant force of 1.5 G, which is positive now because it's going downwards, and upwards is negative, minus T. And it's equal to MA, 1.5A. Voila. So this is your equations of A and B. Now, we have to try and solve this to find the value of the acceleration. We don't care about the tension, which is alright, I guess. And to find this, it's just simple simultaneous equations. What I did is that I decided to just add both equations together. Because if you add them, the T values cancel out, because T minus T is 0. And then you're left with 1.5G plus minus 12.7. So I left it over here. And then 2.5A plus 1.5A is 4A, and then divide by 4, and you have your acceleration. So that's literally part A and B done. So easy. Now let's look at C. So like I said, guys, this is a very simple question. Now using the model, find the time it takes from release for B to reach the floor. So we know that it's 1 meter away at the moment. So what I did, I resketched this diagram as over here, and I'll explain it. So here's the particle B right now. So we know it's the distance 1 meter from the floor, so we can firstly say that the distance S is 1. We know that it's released from rest. Now this is very important. If it's released from rest, it means that the initial speed U is 0. So here we go. We know that the acceleration is constant and it's going to go down at an accelerating, it's going to accelerate at 0.5 meters per second squared, so that's at A. We don't necessarily need to know the final speed as it touches the ground. We just care about the time T. So firstly, so what you should always do is write a set of SUVA equations. Yeah, so write SUVA and fill out your variables. S is 1, U is 0, V we don't need, cross it out. A is 0.5, and we're trying to find T. So we have 1 unknown and 4 terms, which is perfect. Now finding a suitable SUVA equation, pick one that doesn't have V in the formula sheet, and you should come to this one. S equals UT plus half AT squared. And just pop in all your values. So S is 1, U is 0, so that cancels out. And then half AT, half times 0.5 times T squared. And then tidying all this up, you get quarter T squared, or T squared over 4 equals 1. Timesing 4 across and square rooting. And your final time it takes for the ball to hit the ground is 2 seconds. Done. Easy. Yeah, so we're almost done. Now, let's look at the final bit, D. Okay. Now, D is very straightforward. I'm going to just leave it so you guys can see it. So suggest 2 improvements that could be made in the model. Now, this is very just common sense. No, not common sense, but this is just depending on what you understand about the forces in general. Now, one thing I always use for these questions is the gravity value G. G is fixed at 9.8, but to get a better result, a more accurate result, it's better to use a less simplified value. For example, like 9.81 or something that isn't too approximated. You always want to improve the value of G by picking the one with the least number of rounded figures. So that's one. So I wrote here, what did I write? Use a bare approximation to the G value instead of 9.8, simple. And I also talked about the ball. Because we don't know much about the ball, we model it as a particle. And something as a particle has no weight. But if we get the ball actual dimensions, okay, it's a lie, it is a weight. If we get the ball actual dimensions, then it would actually change for example, the speed of the ball falling down. So some things with actual dimensions will actually affect the ultimate run of the ball. So I wrote here, ball, add dimensions so falling distance can be calculated more accurately. There's other things you can discuss, for example, the surface itself being rough. We want to know the actual coefficient of friction here, and maybe it's rough at different places. Maybe the pulley as well, if it wasn't parallel or if it was in a different position, the ball distance will fall. There's quite a few things. And oh yeah, something they don't mention is air resistance. If there was air resistance, then that might affect the drop as well, and so forth. That adds another drag. It's like another type of friction again. So there's various types. I mean, they just want 2. So, and the easiest one is the value of G being better and the dimensions of the ball. Simple. But yeah, guys, if you enjoyed this video, please give me a like as always. And otherwise, I'll see you guys down the road, innit? Take care.